So we're going to talk a little bit about stocks today, the value of Apple stocks specifically first. Stock prices from the day to day, making investments risky. Sorry, stock prices vary. That's what the word says. How can we analyze the value of stock over time, and how could this help us make predictions for what will happen in the future? So the value of Apple stock over a 14-day period can be modeled by this graph in red below, A of T, where T is representing the days after May 31st, and A of T is measured in dollars. So that red function there, those are all the dollar amounts at specific days after May 31st. Okay, so this is our graph below. I would like you guys to label on the x-axis here, or the T values. This right here is May 31st. Okay, so every point to the right of that are days after May 31st. Okay, so like this right here, that would be June 1st.
Wait. Yeah, it's hard.
You don't need to write all of them down. I just want you to know that from May 31st, one away from that is 1 day past May 31st. It doesn't just mean one, it has a value behind it, okay? It's actually on June 1st. Okay? So we're going to kind of answer some of these questions and just use kind of the knowledge that you guys already have of looking at graphs and analyzing things before we talk about the calculus part of it. Okay? So what I want you guys right now to talk with the person next to you about, or feel free to write it down, is to describe what is happening with the value of stock over that 14-day period. Try and be specific with maybe certain days that might be important. What's happening with the money of the stock at certain days? So what's happening over this 14-day period? Okay, we could say something like the money is fluctuating. Okay, that's like a pretty generic thing, right? It's going down, it's going up, right? Fluctuating. That's what that word means, right? It's lower on certain days, higher on certain days. You could say things like it decreases to the first day all the way down to a certain value of, I don't know, like 205 or 206. And then it increases a few days later up to this value of 217. However you want to kind of explain that is fine, just to kind of get an idea of what's happening with those Y values. Those Y values are obviously increasing and decreasing at various kind of increase and decrease speeds, okay? So next question says, what is the highest value of stock during this time period, and what is the lowest value of stock? So go ahead and answer those questions. Check with your neighbors, see if you got the same thing as them. All right, our highest value should be right at the beginning, $226. And the lowest is 185 approximately. You guys might be off by 1 or 2, that's fine. Okay. Again, we're not talking about any calculus, just kind of looking at this graph and analyzing it a little bit. So question 3 says, suppose you bought stock on June 1st. What was the highest value your stock reached during the first week of owning it? And how does that compare with my answer to question number 2? So June 1st is obviously right here. And then a week from that, 7 days. So 1, 2, 3, 4, 5, 6, 7. So we're looking at this kind of interval right there. What is the highest value in that first week?
A little over 216.
A little over 216? Want to call it 217 maybe?
Yes.
Okay, so we'll call it about 217, or you could call it 216.50, whatever you want to call it. I'm going to call it 217. And how does it compare with our answer right before?
About 10 less.
It's about 10 less, right? It's not quite as high as our starting stock value.
I thought that was just the highest. Well, it is the starting.
Okay, next question is a little bit of calculus. We got to think, how fast is the stock moving? When it's moving the fastest, and how do we know? Any ideas? Yeah, it's when it's the steepest on the graph, right? So there's kind of 2 different spots where it is the steepest on the graph. Probably the steepest over here on the left, in between 0 and 1. And then where else?
Day 13.
Yeah, day 13 and 14, okay? So we could just go ahead and say between day 0 and 1 and day 13, and 14. And we know that because our slope is the steepest. And the last question is, for what values of t is the value of the stock not changing, and how do you know? So if we go back up here and look at our graph, where is the stock stationary for just the tiniest second before it shifts?
About 1.25.
Yeah, at about 1.25, so about this point right here, right? Where else?
3.7.
Yeah, about 3.7 or so. There's two other points.
12.7.
Yeah, 12.7 or so. And there's actually one other point. Yeah, the flat part right there. Okay, if I look at all of those points, the slopes of all those tangent lines are actually equal to what?
0.
0. Okay, so that's how we know that the values of the stock are not changing at those values. Okay, so I'm just going to say approximately what you guys just said, so like 2.5. I don't know, it was like 3.7. Wait, isn't it like 1.5 actually? Yeah, it's like 1.5, but that's okay. Let's do 1.5. 1.5, 3.7, about 9, and then 12.7. Okay? And that is when your slope is 0. Or when you have a horizontal tangent line at that point. Okay, so we're going to go and we are going to go write some notes on the top of the next page before we come back and kind of apply some calculus terminology to what we just did. Okay? So, some important ideas here. This EVT up on the top stands for extreme value theorem. Okay? Extreme value theorem. Okay, not to be confused with intermediate value theorem. Extreme value theorem is different. So let's go ahead and write a definition of what that means. I'm just going to abbreviate EVT here. Extreme value theorem is if we have a function f of x that is continuous on an interval a to b, then our function f of x must have a minimum and maximum value on the function, or on the closed interval a to b. Let's go ahead and write down those relative minimum, relative maximum kind of definitions here. And then we'll draw a picture on our paper as well. So f of x has an absolute maximum at a point x equals c if f of c is greater than or equal to f of x. That means if my y values that are really close to that point are larger than the y values around that point for all x on the graph. Okay, I'm going to draw just a quick sketch of a graph up top here so we can label some of these things on here as well. let's say I got this point. Oops. Yeah, that works. Okay. So our absolute maximum on this graph that I just randomly drew would be at this top point right there. Can you see that? Maybe I'll choose an actual color green. That point. Okay. Now, if you're on Notability, you can copy and paste that statement 3 more times down below it, and we are going to kind of erase certain words and then rewrite them. However, since Explain Everything does not have that function, I have to rewrite it. So just bear with me for a second while I start writing the new statement about our relative maximum. So f of x has a relative, that's your word you're changing, maximum at x equals c if f of c is still greater than or equal to f of x, but not for all x this time. It's going to be for x near c. So change those 2 things that I got underlined there. And then if I was looking at relative maximums on my graph here that I randomly drew, a relative maximum would be at this peak right there, because really close to those values, the y value at the top is bigger than the y values next to it. Another relative maximum would be right there. Had a little bit of a divot there next to it. Again, it's higher than the ones on the left. And then the last relative maximum would be this point right there. Okay, we've talked about maximum, now we gotta talk about minimums. So, again, I'm gonna write it, you can have copied and pasted it, but f of x has an absolute minimum at x equals c. Oops. So minimum is the word that you gotta change there. If our function f of c, now my y values would have to be less than, so I need to change that symbol to be less than or equal to f of x. And we can keep for all x. So if I go back up to my picture that I drew, I've got 2 points where I've got I've got 1 point where there's an absolute minimum. My absolute minimum is the lowest point on the graph, which would be down there in the middle. But I will have 2 points where I have a relative minimum, and those 2 points would be on the other 2 lower points on my picture there. Okay, so that's our last statement that we have to write, is f of x has a relative minimum at x equals c if our function f of c still is less than or equal to f of x, and then for the x near c. So for all the x values near the point that I have my relative minimum, those are all going to be larger than the point down on the bottom there. Do you guys feel like you could identify some relative minimums, relative maximums, absolute minimum, absolute maximums? Good. Okay. Then the last thing that we need to say on here for the important ideas is the certain points where we have slopes or tangents horizontal that are, we have slopes, we have tangent lines that are horizontal, which have a slope of 0, right? We call those critical points. So critical points are pretty important in calculus. It allows us to test a bunch of different things. So we can find critical points when my slope is equal to 0, or when the derivative is equal to 0. So critical points are points where the derivative is 0 or undefined. How do I know if a derivative is undefined? Well, if it's 0, it's 0, right? If the slope is 0. But, like, how would I know if it's undefined? If I have what? If you have, like, a vertical line?
Indeterminate form.
Yes. Kind of, I think is what, I think I know what you mean. Like, if you have something, think about, like, the safe versus unsafe. If you have something that goes like that, right? This is a point where the slope would be undefined. Or if I have a function, but I have a hole at that point, that's another point where it's undefined, so that's another critical point that we would have to test, okay? And we can get holes by looking at functions if we have, like, the numerator and denominator cancel out, right? That's how I can identify holes in functions and things like that. So we're going to do the first 3 of these problems down below to kind of see if we kind of understand what's going on, and then we'll talk about the next homework or next notes page over the candidate testing, which uses all this information as well. So we've got a graph here for number 1, but specifically the graph is of my derivative. This is my derivative function. This is not function f of x. This is the derivative. So what values of x does f of x have critical points? So think, when do I have critical points? I have critical points when the derivative is 0 or undefined, right? So when is my derivative equal to 0 on this graph? This is my graph of the derivative. So where is it equal to 0? 1 and 3. This is 0 at x equals 1 and x equals 3. Okay, so at x equals 1 and 3, I'm just going to kind of write a little note here. This is when our derivative is equal to 0. Now there's one other point on this graph that is considered a critical point.
4.
At 4. Right here at 4, I have an open circle. Okay, so that's a point that is undefined. So 4 is when f of x, or f prime of x, I should say, is undefined. Okay, next question says, let g of x equal 3x squared minus 8x plus 7.5, and we need to find the critical points of g of x. So, find the critical points means I need to take the derivative and set that equal to 0. And I need to figure out when is it undefined. If I have like this graph, what does this graph look like before we start taking derivatives? 3x squared minus 8x plus 7.5. It's a parabola, right? Is a parabola ever going to be undefined? No. Okay, so I don't have to worry about that. But I do have to worry about when is my parabola, right? When is the bottom of that equal to 0 at that tangent line, okay? So I got to take the derivative of this function, and I get 6x minus 8. And now I'm going to set this equal to 0. So quick little 2-step here. I can solve to get 6x equals 8 and x equals 4/3. So our critical points are 4/3 that we would have to check. And again, at 4/3, I'm just going to kind of draw a quick sketch of my graph g of x. It's not going to be perfect, but I think it looks something like this, and it's not perfectly there in the center. But it's going to be a parabola, and this point is x equals 4/3. Okay, that is the point that is changing my derivatives from negative over here to positive. Okay, critical points are points where the derivative changes from one sign to the other. Okay? All right, last thing to make sure that we all kind of understand what's going on here is I want you guys to all try and sketch a function on the interval from -3 to 8 that meets the following requirements. So it has to have these 4 things on your graph We are not doing number 4 because we have not talked about the mean value theorem yet, so you can't answer that question. So go ahead and try out number 3. Draw a graph and check with your neighbor, see what theirs looks like, and then I will give you an example as well. The important things is that it has to be starting at -3, and then it has to end at 8.
Wait, it starts at -3?
Yeah, it says that.
Has to?
It says -3 to 8.
Oh, I didn't see that.
That's okay. And then it says that there is a absolute maximum at the left and relative minimums at -1 and 3. So -1, I'm going to put 1 there, and at 3, I'll put 1 here, for example. So let's see. My relative maximum is on the very far left. So I could go something like this is now a relative minimum. But I have to go back up to go back down to another relative minimum. But it has to be a minimum, so that means I have to go up a little bit here. But what has to happen at 4? It's got to be undefined, right? So I'm going to have like a hole somewhere here at 4. And then it says that the absolute minimum is at x equals 6. But again, it still has to go to 8. So absolute minimum is at 6. So 6 is here. So I don't know, let's put it down here. So I'm going to go down. And then it can go anywhere, but it has to stop at 8. So I'm just going to stop it right there. Okay? Yours might look a little bit different, but as long as you have some peaks and valleys there, you are good. Okay? Sound good? All right. We are not going to do number 4. So cross that one out. Oh, and then we need to go back really quick and just look at the first page again so we can kind of see where these relative minimums, relative maximums come from that first page. Okay, so back to this first page here. On number 2, okay, number 2, the highest and the lowest values during this entire stock period, the highest and lowest values completely, those are going to be our absolute max, absolute, and our absolute min.
Can we, like, abbreviate?
Yeah, you could do like ABS dot. And we know that we have to have an absolute and we have to at least have a maximum and a minimum if our function is continuous, because our function a of t is continuous. So must have a max and min on the interval 0 to 14. Okay, since we're on a closed interval, it's continuous. It has to have a min and a max. Now, 217 that we found in number 3, that is not my absolute maximum, but we would call that a relative maximum. And then critical points come into play for number 5. Number 5 is what our critical points are on this graph. It is at all of those points where the derivative would change from positive to negative, okay, or where our horizontal tangent line, right, has a slope of 0. Okay, so critical points again are where our derivative is equal to 0 or it is undefined.